Okay, we're going to continue talking about radical expressions, but we're going to take it one step further and start looking at rational exponents and how they relate to the radicals we've been talking about. So, if we were to take x to the 1/2 power, like you see here, and we were to square it, let's think about what that would do. So when we raise a power to a power, think about the exponent rules. When we raise a power to a power, we multiply those powers, right? So this becomes x to the 1/2 times 2. If we multiply 1/2 times 2, that's like 2 over 1. We can simplify that. We're just going to get x, right? So if we square x to the 1/2 and we get x, what did x to the 1/2 have to be so that when we square it, we undo it? It had to be the square root of x, right? So rational exponents are a way that we can express radical expressions through exponents. Okay, so x to the 1/2 is equal to the square root of x. Here's the book's definition of b to the 1 over n. So b can be any number. And then positive integer, right? We're still talking only about positive exponents. We'll get to negatives later. Then b to the 1 over n means the nth root of b. So if I have 6 to the 1/3, that's the cubed root of 6. If I had 27 to the 1/5, that's the 5th root of 27. If b is less than 0, so if b is negative, then we might get a complex root, right? So look at this example right here. We've got negative 16 to the 1/2. That's the square root of negative 16. Right? Square root of 16 is 4, but we have a negative 1 in there, so that's where the I is going to come from. So the square root of negative 16 is 4i. If it's an odd root, right, we don't have to have complex numbers. So if it's the cubed root of a negative number, we're just going to get a negative root. It's not going to be complex. We'll come back to that later. So we're going to write rational expressions as radicals and radical expressions as rationals. So we can go take this both ways. So let's start easy. X to the 1/6. Base is 6, so that's the index of my root. I want the 6th root of x. Okay. Let's look at this one. 4th root of w. Well, that means it's w to the 1/4. Now it gets a little bit different when we have a numerator that's not 1. So think about that as a to the 7th, excuse me, a to the 7th and a to the 1/4. So a to the 1/4 means the 4th root of a, but a to the 7th means a to the 7th. Okay, so that's the key right here. The numerator is the exponent on the radicand, and the denominator is the root. So this guy, the cubed root of p to the negative 5th power, is p to the 3rd, right? It's going to be in the denominator, negative 5/3. So 81 to the negative 1/4 is the 4th root of 81 to the negative 1. You could also write this with the negative 1 all the way on the outside. And the negative exponents mean we just want it in the denominator, right? So that's 1 over the 4th root of 81. 4th root of 81 is 9, so that's just 1/9, right? We can't leave radicals in the denominator. We have to rationalize those. So we'd want to keep going. Luckily, 81's a perfect 4th, so we didn't have to do any work there. Okay, so hopefully you kind of have a feel for how we go back and forth. I'm going to write a general form here real quick. Let's do this. Let's say we'll call any number b to the a over n is the nth root of b to the a. Right, so you can kind of just see how things move back and forth. We can do a numeric example. Let's say 12 to the 4/7 is the 7th root of 12, and the whole thing is raised to the 4th power. So go ahead and pause this if you want to get this in your notes. That would be a great idea to have this little formula, I guess, if you will, to go back to. Okay, the future cost of an item due to inflation can be estimated using a formula, right? So the only variable here is the rate of inflation. If it's interest, then it's easy, but inflation can change a little bit. Remember, inflation is when the value of money goes down. For example, gas, right? When I was in high school, gas was under $2 a gallon all the time. And since then, I've seen it all the way up to $5 a gallon. It's back down right now, but in general, the value of a dollar goes down. The costs of things continually go up just because the dollar loses its value slowly over time. That's inflation, when costs are artificially inflated. So, following formula where C represents the future cost, little c represents the current cost, R is the rate of inflation, and N is the number of years that we want to project it out. So, suppose a video game costs $390 now. How much would the price increase in 10 years with an annual inflation rate of 2.2%? It's really important to recognize that we are not talking about the value of this thing going up. It's just the cost of it, right? A brand new truck now is going to cost you $40,000 to $50,000. A brand new truck in 1980 maybe $15,000 to $20,000. Now, does that mean that a brand new truck from 1980 is now worth $50,000? No, those values have gone way down, right? You could get a truck from 1980 for probably $1,000 now if you wanted to. So we're not talking about the value of the thing. We're just talking about how the price of that object may have gone up or down. So video game costs $390 now. How much would the price increase in 10 years? So the future cost, I don't know. Current cost is $390. 1 plus the rate of inflation. Now we got to change that to a decimal, so that's 0.022 in 10 years. So get your calculator out. This is 390 times 1.022 to the 10th. It's really important that you raise this number to the 10th power before you multiply by 390. 1.022 to the 10th. I get 1.24 times 390. The cost of this thing in 10 years should be roughly $484.81. Again, I'm not saying that this video game system is going to increase in value. If you buy one now, you're not going to be able to sell it for $484. But 10 years from now, when the replacement console comes out, it'll cost probably this, assuming everything else is consistent. Let's test this. In 1988, the Nintendo Entertainment System Action Set was released for $149.99. This included 2 controllers, the Zapper, Mario Bros, and Duck Hunt. If you guys have not played Duck Hunt, you're missing out. This is like the first big video game that really exploded. This is after the Sega and the Atari, but this is Nintendo's introduction. So how much would this system cost now due to inflation, assuming 2.2%? That's kind of the national average for inflation, is 2.2%. So let's say future cost is the current cost, so 149.99 is the quote-unquote current cost, times 1 plus 0.022 to the, well, this is 1988. Let's say it's 2020 right now, so that's 20 years plus an additional 10 years, so that's 32 years, right, from 1988 to 2020. Calculator, 1.022 to the 32nd power times 149.99, $300.95 is what I'm getting. And what's interesting is the Xbox One starter pack, Xbox One S, which came out in like what, 2018, 2019, $299 manufacturer suggested retail price. That's what MSRP stands for. So take a look at those two numbers. They are, for all intents and purposes, the same. So what's kind of interesting is the cost of video games has not really gone up, right? That's what inflation does. It just makes the price artificially go up. So in 1988, you could have this set for $150. Now, this same set is probably equivalent to an Xbox One S starter pack. It's going to come with 2 controllers, 2 games, the console, $300. It's the same price, right? Technology's improved, obviously. The price of this has doubled, but salaries, home values, the cost of gas, the cost of milk, the cost of bread, that's all basically doubled. So this cost of the Xbox One is going to be the same percentage of your income as the Nintendo Entertainment System starter pack would have cost back in 1988. It's the same chunk of your money. It's just that all of the numbers have gone up a little bit. So that's obviously one application of exponential manipulation is inflation. I want you to take a minute or two, pause this until you've tackled all 4 of these. We're just simplifying these. So writing them as radicals and then simplifying as much as necessary. So pause this for 2-3 minutes and then come back when you're done. Okay, we're going to tackle these one at a time. Let's start over here. A to the 2/7 times a to the 4/7. When I multiply powers, I add exponents, right? So I need to add 2/7 and 4/7. That's going to be a to the 6/7. They have a common denominator, so I can just add. So that is the 7th root of a to the 6th power. And that's as simplified as that's going to get. Okay. Let's jump down here to the p's. P to the 1/4 times p to the 9/4. That's going to be p to the 10/4, which will be the 10th root of p to the 4th power. That's 4, not 9. Okay, again, can't reduce that any further. Now's where it gets slightly more tricky. B to the negative 5/6. Well, that's the 6th root of b, and the whole thing is to the negative 5th. So that means it wants to be in the denominator, so that's 1 over the 6th root of b to the 5th, right? The problem is I can't have radicals in the denominator, so I'm going to have to multiply some stuff here. So what I really have is the 6th root of b to the 5th power, right, under 1. So I just need to multiply by 1 more 6th root of b to make that 6th root of b to the 6th, and that's something that can be simplified. So I'm going to multiply top and bottom by the 6th root of b. So the bottom now is the 6th root of b to the 6th, and the top is the 6th root of b. These cancel, and what I end up with is the 6th root of b over b. A little bit more work because we had a radical in the denominator. Let's try one more here. I'm going to change colors and do this out of the way so we don't get confused. That's the 5th root of r to the negative 4th. Negative exponent means put it in the denominator, so that's 1 over the 5th root of r to the 4th. So I've got r to the 4th, but I need groupings of 5 if I'm going to simplify that. So to rationalize it, I'm going to multiply by the 5th root of r, 5th root of r. The reason I'm doing 5th root is because to combine these radicals, I have to have a common like term, so they have to have the same index. And the reason I'm using an r is I'm trying to make this exponent on the r get to 5 so I can take the 5th root of r to the 5th. I have 4 r's, I only need one more, so I'm going to multiply by the 5th root of r. So the denominator becomes the 5th root of, and I can multiply the radicands, so r to the 4th times r is r to the 5th. And that's what I want. I want those two numbers to match. So up here I just have the 5th root of r. So my simplified answer is going to be the 5th root of r all over r. Okay. Again, you can rewind this at any point. Hopefully it all makes sense. A little bit of a summary here. An expression with rational exponents is simplified when all of the following conditions are met. So if something is simplified, a rational expression is simplified if these 4 things are true. It has no negative exponents. It has no negative exponents in the denominators, right? So no exponents that are not positive integers. So no negative exponents in the denominator. It is not a complex fraction. Complex fraction is a fraction made up of fractions. And the index of any remaining radical is the least number possible. So we don't want deeper roots than we need to take. Okay. Good luck on the homework.